Hello, today we will be doing homework 3 part B, and first we will be driving the closed loop transfer function for a series of 3 gravity drained tanks with a proportional only controller. And so from the last part of this homework, we know that we had a transfer function that was in the format of k over tau s plus 1, with k being the gain and tau being the time constant of the system. And so we can kind of redraw our situation or draw it in a way that will fit our problem here, because we want it to be in the form of a loop. So we have a Q in, a flow rate going in that is transferred or converted to this height coming out, or not I, but height 1, so the liquid level of the first tank. And so in order for that flow rate to convert to the height of the first tank, it is multiplied by a transfer function. And then in order for the height of the first tank to change into this Q1, this flow rate coming out of the first tank, it would be multiplied by the reciprocal, or the reciprocal of our gain. So it'd be 1 over k. And it kind of just keeps repeating through all tanks. So in order to get this height of the liquid level in the second tank, it'd be multiplied by our transfer function again. And then it would be multiplied by 1 over our gain again. I'm going to move this over. And then we get the flow rate coming out of the second tank, which is then multiplied by our transfer function to finally get H3. So if we look at this whole process of getting from our flow rate in to our final height of the liquid level in the third tank, we can draw a boundary here around this whole process, and we can define this as P, and we can say that Q in, we can just kind of generalize this whole process as just its own transfer function, which we can call GP. And so it goes through all of that to get to H3. And the way that we define GP, the way that we can define this entire transfer function, is by multiplying all of the transfer functions together that are moving in the forward direction. So GP will equal, so we have 3 of these transfer functions here. So we would have k over tau s plus 1 to the third, and we have 2 of these 1 over k. So it would be 1 over k to the second. And so if we simplify that out, that will equal k over tau s plus 1 to the third. So that is what our GP function is. So that's just our way of representing this whole process inside of our boundary here. And then we also, from the problem statement, we want to add a proportional only controller into this. So to add that to our system here, we're going to add another function down here. We'll call it GM. And we'll have it kind of come down here. So it'll take the height, it'll take feedback from what this height is coming out of, and it'll send feedback up here that will allow the flow rate in to increase or decrease based on how close this height is to its set point. I'm going to decrease this a little bit. And so what comes out of this signal right here is our error, which we have talked about in previous homeworks. Just the difference of the liquid level that we want versus the liquid level that we actually have. And so what comes out here is going to be our controller gain. We typically have called it KC in other problems, but we're going to call it GC. And so let's look at our error. What is our error? So our error is, so we have an H3 going to a GM. So it would be H3 times GM minus our set point here. And we know that H3 equals these other functions that are going in the forward direction, GP, GC, and our error. So H3 will equal GC times GP times our error. And so we can plug this equation here into this equation. So you'll get H3 equals GC times GP times the height of our liquid level in the third tank times our transfer function that is taking into account the height of our third tank and sending a signal to change our error minus the set point that we want. And so we can expand this out to get H3 equals GC GP GM times H3 minus GC GP HSP. And we want to isolate H3. So we can get H3 and we'll subtract this term to the other side. So we'll get H3 equals 1 minus GC GP GM. That will equal negative GC GP HSP. And we can divide this side by this term here, and I want to get rid of this negative here, so I will flip the sign over there to a plus. So we'll get H3 equals GC GP, and then I'll put our set point on the outside over 1 plus GC GP GM, and then here's our set point. So what we have here is a transfer function that is converting our height set point to our liquid level in the third tank. So this is our transfer function here. And this is our closed loop expression, and this is our closed loop transfer function. So if we look back at what this really is. It's just the transfer functions that are going forward. They're going forward to H3, so G forward, just divided by 1 plus all of our transfer functions in an open loop. So say it's open. These are all of our transfer functions moving through this open loop. So G of our open loop. And yes, I believe that is part 1. And so for part 2, we are going to use the final value theorem to show that with this proportional only controller that we've implemented here, the height of the third tank is always going to have an offset relative to our HSP that we can reduce by increasing our controller gain. Our controller gain, which we have represented here as GC. So let's start by looking at what the final value theorem states. The final value theorem states that as our Laplace transform variable approaches 0 of this function here, it's equal to the limit as time approaches infinity of this function. So if we apply that to our situation that we have, we can say the limit as s approaches 0 of sh, with h being our height. So h will be our height, and then its deviation variable will be h prime. So this will equal the limit as s approaches 0 of this closed loop expression that we have just derived. So of GC GP over 1 plus GC GP GM. And HSP is already a deviation variable, but to express it, we want to express it in a different way. So if we look over here, HSP is basically, it has a step here that we're going to call A, and this step is, it's being increased or decreased by this right here. So we can express this step as A over S. So that's what we're going to put here instead of our HSP, because that's deviation variable already. So if we look at the expression we have here, we can see that these two s's actually cancel out. And so what we're left with is the limit as s approaches 0 of h equals the limit as s approaches 0 of GC GP A over, so you're gonna put that outside of the fraction, plus GC GP GM A. So how do we move on from here? Well, we have an expression for GP. We know what GP is. We defined it up here. So GP is that expression. It is our overall transfer function for this entire process from Qn to H3. So let's look at the limit as s approaches 0 of just our GP function. K over tau s plus 1 cubed. So as s approaches 0, this term here goes to 0. So we end up with k over 1 to the third, which just equals k. So we can actually replace our GPs here with k. So I will rewrite it. GCK plus GCK DMA. So what we'll notice here is, so this expression, this equals h. That's what we have right now. And if we notice, we have these two terms here, and we have these terms, we have them in both the numerator and the denominator. And we'll see that this term right here, this fraction, will never exceed, it will never equal 1, and it will never exceed 1. It's always going to be less than 1. And this a term, that is part of our set point. So if we look at that value as our set point, and we look and we see that our set point is always being multiplied by a value less than 1, we see that our h out, our h3, is never quite reaching our set point. So we can see that this proportional only controller is always going to produce an offset that is relative to our set point here. So how can we get our liquid level of the third tank, how can we get it as close as possible to our set point? Well, we need this fraction to be as close as possible, as we can get it to 1. So if we look at the limit as k approaches infinity of just this term here, we can see that our k's here, those will go to infinity. So this one, basically, this one is nothing in comparison to infinity. This one means nothing. And these other non-negative terms, GC and GM, will also pretty much be nothing multiplied to infinity. So it ends up just being k over k. So as k approaches infinity, this term, or this fraction here, approaches 1. So the larger that we make our k value, the larger that we make our controller gain, the closer our height will be to our set point. So as our controller gain, as it increases, as k increases, our height of our third tank will move towards our set point. So it'll move towards what we want it to be. So yeah, the offset relative to our set point will be reduced when we increase our controller gain of kc, or of k, as we have shown here. Thank you for watching.